Well, hello physics folks. Welcome to Doc Onco Physics. Keith Onco here. Today what we want to look at is another one of Newton's laws problems. And what we have is we have a block on a table connected by a string or a rope or a cable to another block. So we have a block M1 up here. Whoops. We have a block up here and we have another block up here, over here. And they're connected by a cable. All right, but one is acting in a vertical sense and one is acting in a horizontal sense. Okay, there's really no difference to the problem that we have out on the internet where two blocks are connected by a cable and they're both on a surface and they're being pulled by, or one of the blocks is being pulled by an external force. This time we have really the same situation, but many students get confused by this type of a situation. All right, so once again, what we're going to do is we're going to look, first we're going to identify each one of the objects in our system. All right, so the first object is going to be M1, okay? And the second object is going to be M2. Now, let's look at the forces we have on block M1. Well, we have our force due to gravity, okay, which is going to equal M1 times G. We have the normal force, I'll call that Fn1, and that's also going to be equal to M1G, except it's going to be positive. I'll put a 1 down here as well. All right. We have a cable attached to M1, all right, so we're going to have a pulling force on that cable. We're going to call that T, okay. And there's no friction, because we haven't said anything about friction, so those are the only forces on block M1. Let's look at block M2. Well, we have the force due to gravity on block M2. We'll call that M2 times G. All right? And we have the tension in the cable pulling on the block. Right? So that again is going to be tension because it's all one rope or one cable, so the tension is the same throughout the cable. Okay? Do we have a normal force on block M2? We do not. Right? You only have a normal force when the object is sitting on a surface. Okay? If it's not sitting on a surface, there's no normal force. Okay? So these are the two blocks that we have. Now, the coordinate system that we're going to use for this block is going to be x and y like this. And the coordinate system for this block is also going to be x and y, right? Except that the forces that are going to be of interest to us for block M1 are going to be the x forces, right? The y forces essentially cancel each other out, right? If we write our equation for the y forces for block M1, it's just going to be Fn1 minus Fg1 equals 0 because there's no acceleration in the y direction, and so we don't get really any good information here. Okay. However, for block M2, what we are interested in is the y forces. Okay. So we're interested in the x forces for block 1, all right, x forces for block 1, and the y forces for block 2. So those are the equations that we're going to be writing. So let's do that. Let's write the forces, all right, the sum of the forces in the x direction for block M1. Well, what do we got? Well, we have tension, all right, the tension in the cable. And we have nothing else in the x direction. We have no friction, haven't said anything about friction yet. All right, and that's it. So what's that going to equal? Well, it's going to equal M1, I'm sorry, times A1. And that's it. We haven't given any numbers for the masses yet. We'll do that in a few minutes. All right. Now let's look at the sum of the forces in the y direction, for block 2. All right, sum of the forces in the y direction for block 2. What have we got? Well, we've got negative M2G because it's going downwards. All right, so negative M2G, okay, plus T is equal to what? Well, it's equal to M2 times A2. Okay, now, question we've got to ask is, what's the direction of the acceleration going to be for block M2? is block M2 going to be moving up or is it going to be moving down? Well, since there's no friction between M1 here and the table, right, block M1 is going to be pulled to the right. If block M1 is pulled to the right, that means block M2 is going to be going in the downward direction. So we need to stick a negative sign in front of the A2, okay, because that's going in the downward direction, right? So it's negative A2. Now, just like in the other problem that we did where two objects were connected by a rope or a perfect cable, right, where a perfectly massless cable, no stretching involved, when one block accelerates, the other block will accelerate at the same rate. So we can get rid of, we'll do that right now, I will erase this, we can get rid of our subscripts, okay? And so the acceleration for one block, the magnitude of the acceleration, is the same as the acceleration for the other block, okay? So what can we do here? Well, we have t equals ma up here, all right, m1a, I'm sorry, and we have negative m2g plus t equals m2 times negative a down in our second equation. We can substitute m1a in for t right there, right? That's perfectly valid. Or we can multiply the top equation through by negative 1, right? And then add the two equations. Either one works. They both amount to the same thing. Since I did the adding of equations in the last problem, what I'll do is the substitution in this problem. So let's substitute in for t, right? We're going to substitute t, which is here. We're going to substitute m1a in for t. All right, so we can end up with this negative m2 times g plus m1 times a, all right, is equal to m2 times a. But remember, there was a negative sign in front of that a, and so I'm going to stick that negative sign right there. Okay, I'm going to move it out to the front. So what can we do? Well, I can subtract m1a from both sides, and I end up with negative m2g is equal to negative m1a minus m2a. I collect my terms on the right-hand side, and I get negative m2g is equal to, negative a times m1 plus m2. All right, the negative sign distributes, all right, so we're good there. All right, now the only thing we don't have here yet is we don't have what the values for our m1 and m2 are. So let's assign some values here. Let's say that m1 is equal to 2 kilograms, and let's say m2 is equal to 4 kilograms. So m2 equals 4 kilograms. And now we can just plug in some numbers. So let's go over here. So negative 4 kilograms, that's m2, times g, which is 9.8 meters per second squared, is equal to negative a, which is what we're trying to find out. Negative a, looks more like a 9, but it's an a, times m1 plus m2. Well, m1 plus m2 is going to be 2 kilograms and 4 kilograms, so that's 6 kilograms. Okay? So negative 4 times 9.8 happens to be 39.2 newtons now, is equal to a times 6 kilograms. All right, if I divide each side by 6 kilograms, I get, let's see, 39.2 divided by 6 kilograms is 6.53 meters per second squared. So that's A, okay? So we found A. How do we find T? I'd like to know T, all right? We find T simply by plugging in A to the simplest equation we have. Well, the simplest equation is that one right up there, all right? So T is equal to m1, which is 2 kilograms, times A, which is 6.53 meters per second squared, and 2 times 6.53 is about 13 just about 13 newtons. So that would be the tension in the rope, right? The tension in our rope is about 13 newtons between those two objects. So remember that in any one equation, right, in the top equation, I could only have x data or y data. I can't mix x and y data in the same equation, right? So the first equation had only the x data for block M1. The second equation had only y data for block M2, right? Can't mix x and y data for block M2 either, right? But once I've written the equations, then I am free to add those equations together or substitute or do or whatever method you'd like to use. Okay, I can't have multiple types of data in the same equation. Okay, they have to be either x or y, right? But once I've written the equations, I can then add those equations regardless of whether they were in the x dimension or the y dimension. So I hope that's clear. Well, I hope that helps, and have a great day.